welcome everyone. In this example, I want to look at how we can calculate the standard Gibbs energy of a reaction using the standard molar entropies and the enthalpies of formation. Alright, so we're given a reaction and we're asked to calculate the standard Gibbs energy of reaction. And hopefully you recall that the standard Gibbs energy of reaction is equal to the enthalpy of reaction minus T times the entropy of reaction. Well, at least that's one of the ways that you can calculate. Of course, the other way that you can calculate it is through the standard Gibbs energies of formation. But the reason I want to go this method is because the information that we are given in this question is regarding the standard molar entropies and the standard formation enthalpies. All right. So using those information, we can calculate the enthalpy of reaction and the entropy of reaction. So hence, this is the method that we will use to calculate the standard Gibbs energy of reaction. All right, and then we ask some conclusions that we need to make. All right. So the first steps are to calculate the enthalpy of reaction and the entropy of reaction. All right, so let's start with the enthalpy of reaction. To calculate the enthalpy of reaction from the standard enthalpies of formation, we will of course use hopefully something that you've seen a couple of times before, and that is to say, well, that our enthalpy of reaction is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of our reactants. All right, so let's go ahead and do that systematically. So you can write out, so let's first do it for the products. We see our products are sodium hydroxide and hydrogen gas. We have 2 mole of sodium hydroxide, so that means we need to say 2 mole of sodium hydroxide per mole of reaction multiplied by the formation enthalpy of sodium hydroxide in aqueous solution, plus the stoichiometric coefficient, which is 1 for hydrogen gas, multiplied by the formation enthalpy of hydrogen gas. Right, that is the sum of the enthalpies of formation of our products, right, multiplied by their stoichiometric coefficient. And then we do the same for the reactants. So our reactants in this case are water and sodium. So sodium solid, there's 2 mole of sodium solid, so 2 mole per mole reaction of sodium solid multiplied by the enthalpy of formation of sodium solid multiplied by plus the 2 mole per mole reaction of water. So everything of the formation enthalpy of the reactant and multiplied by its stoichiometric coefficient. Enthalpy of formation of the reactant multiplied by its stoichiometric coefficient, same for the products. Okay, and now we just look in the table what these values are and you plug them in. So for sodium hydroxide, it's minus 469.15. For hydrogen, it's of course 0 because enthalpies of formation for pure substances in their standard state, so hydrogen gas, it's in its standard state, is 0. Right? Sodium metal in a standard state, so it's 0. Water liquid is a substance, so it's not a pure substance, a pure element, my apologies, so it will have an enthalpy of formation. So there we go. All right. So if we put in those values, just write it out. And we remember to check the units. So we have mole per mole reaction multiplied by kilojoule per mole. So enthalpies of formation is in kilojoule per mole. The units of a stoichiometric coefficient is in mole per mole reaction. And then you should see that, well, the number of mole cancels with the per mole, and then we're left with kilojoule per mole reaction. So the value for the enthalpy of reaction that I get here is negative 366.64 kilojoule per mole reaction. All right, and enthalpies are usually produced in kilojoules per mole reaction. All right, specifically the kilojoule part is the important part. All right, so that's the enthalpy of reaction. So that's that part. So let's move on to the entropy of reaction. And to calculate the entropy of reaction, we will use this standard molar entropies for given in the table. And we use a similar way of calculating it. It's of course equal to the sum of the standard molar entropy of the products minus the standard molar entropy of the reactants multiplied by their stoichiometric coefficients. So similar expressions to what we did for the enthalpies, right? Stoichiometric coefficients multiplied by the standard molar entropies of our reactants, our products, minus those for the reactants. All right, nothing funny there. All that we now must check now is that we transfer the correct values and units from the table. And what you hopefully notice is that even though things like sodium and hydrogen have standard molar entropies. Why? Because standard molar entropies are what is third law entropies, and they are measured as a reference from 0 Kelvin. Right. So that means what is the entropy of a species at 298 Kelvin relative to what the entropy is of a perfect crystal lattice at 0 Kelvin. And we assume that that is 0. So meaning all materials, all compounds, all elements, all anything will have a non-zero entropy, standard molar entropy at 298 Kelvin, because all matter will have some level of energy dispersion at 298 Kelvin relative to a perfect crystal lattice at 0 Kelvin. Right. So in other words, these values are non-zero. So you must always check that. And of course, we just look them up in the table. So just transfer them from there. All right. I mean, I did transfer them correctly. So yeah, I'll just always double check myself. And going through the mechanics there, you get the value here for the entropy of the reaction. All right. So now all that's left is to, of course, calculate the Gibbs energy. And we plug it back into our original equation, which is the enthalpy minus T delta S. I can actually just correct that. It's the entropy change of the reaction. And we're working at under standard conditions. So that means temperature is 298.15 Kelvin. All right. It's given in the question as well, but that you can always infer that from the fact that we're at standard conditions. And that means we get 362.0 kilojoule per mole reaction. All right. So that is the first part. We're told to calculate the Gibbs energy. Now, the next question is the reaction product or reactant favored at equilibrium? All right, so that's the first question. And then the second part is, furthermore, is the reaction enthalpy or entropy driven? So let's first answer the question about, is the reaction product or reactant favored at equilibrium? And how do we determine that? Well, we need to look at the sign of delta G naught, right? So delta G naught tells us whether or not something is reactant or product favored at equilibrium, or whether or not it is at equilibrium, right? So if it's 0, then something is at equilibrium. So we see that delta RG naught is less than 0, it's negative. So that means we have a product favored equilibrium. Right? So meaning we will have a product favored equilibrium, we will have a large K constant associated with it. With this, you can actually calculate the K constant now for this, but it's not asked, but we have a product favored equilibrium. And then we have the second question about this. Furthermore, is the reaction enthalpy or entropy driven? And the way that we need to assess this is which value, the enthalpy or the entropy, which is quite much larger, and how does that affect our Gibbs energy, right? So we said it's a product favored equilibrium. So that means what value here is causing the Gibbs energy to be negative? And if we looked at it, well, the enthalpy here is the value that's very negative, right? It's the big value that's negative. The Gibbs energy, or the entropy, is also negative, but it is actually causing the Gibbs energy to become more positive. So if we were to increase the temperature of this reaction, then we would cause it to become less spontaneous, right? Or meaning we would cause the reaction to become less product favored, right? Sorry, because delta G naught tells us product favored equilibrium versus reactant favored equilibrium. So if we were to, that is what delta S naught is telling us at the moment. It's actually causing the reaction to become less product favored. So this means that our reaction is enthalpy driven. It is enthalpy driven, and it's because of two reasons. The first reason is that delta RH naught, right, is negative. So delta RH naught is negative, and that is linked to the fact that delta G naught is also negative. So in other words, the reason delta G naught is negative is because the delta H naught is negative. And secondly, the size or the magnitude of delta RH naught is much more negative, much more negative than delta RS naught, right? So at the moment, at this temperature, its impact on the product favored equilibrium, so making this a product favored equilibrium, is much larger than what the effect is of the entropy. All right, the entropy is making this actually, if the temperature were to be increased, then the entropy would become a bigger factor in making this a reactant favored equilibrium. But for at this temperature, the reaction is highly driven to be a product favored equilibrium because of the enthalpy. And overall, the entropy is a very small value. I mean, that's almost zero in comparison to the enthalpy, right? Because what's this? Minus 366, and then you have to multiply by 10 to the power 3, so it becomes 640, and the entropy is minus 15.42. So I mean, what's that? Minus 366,640 versus 15. So I mean, I know definitely which one is driving this reaction to be product favored, and that is the enthalpy. So yeah, it's much more negative than what the entropy is, and so the entropy's effect is actually just because of the temperature. All right, good. So we've covered a couple of ideas here just to calculate the enthalpy of reaction and the entropy of reaction, and then how to calculate the Gibbs energy from those two values. Okay, cool. Thank you for watching. I'll see you in the next video.